Greetings. In this video I want to talk about a simple alternating current or AC circuit. We're not going to cover everything. We're going to leave things like impedance and reactance for another video, but this will be compatible to a previous video I did on a simple DC circuit. So let's get to it. So, talking about the fundamentals of alternating current, well, historically, most electricity generated was DC in the beginning, or direct current. Again, previous video. However, there is an issue with direct current in that it cannot be transmitted over long distances. It falls off pretty quickly as your distance increases, whereas alternating current, depending on your frequency and the voltage, can travel long distances. It's easier to step up the voltage of alternating current also, which also helps in long distance transmission, limiting losses. While DC is much easier to use in our various devices, its power is usually delivered by AC. That's what comes out of the outlet in your house. If you're in the United States, 120 volts. You're in the Philippines, 240. Other places, 240. Japan, 100 volts. But yeah, that's all. It's all AC, and we're going to talk about doing a simple AC circuit and some of the calculations and how they differ from doing DC. So to better understand the AC or alternating current, let's talk a little bit about a simple alternating current generator consisting of a magnet and a coil of wire. We have a little illustration up here on the screen for you to look at. Well, yeah, I'm in the lower corner. It's a screen, but anyway, so when we spin the coil within the magnetic field, when the coil is horizontal to the magnetic field, it's cutting very few lines of force. As we move upwards as we rotate the coil until it becomes vertical with the magnetic field, we cut more and more lines of force, and a electromotive force is generated within the coil, or a voltage, and if there's a complete circuit, then a current will flow. Once we reach the top of the arc and start swinging down, the voltage drops off again, back to zero when we hit the horizontal. Now as we're swinging in the opposite direction, well, same rotation, but it's opposite end of the magnet, the voltage or the electromotive force generated is opposite, and voltage and current will be opposite of what we generated before. So if it was positive before, it's going to be negative in this cycle, this part of the cycle, and as we come back again to the horizontal, the electromotive force drops off, so the voltage and current drop off to zero. And this is basically generates a sine wave, which can go on forever as long as we turn the coil in the magnetic field. So that's basic, plain and simple, how AC is generated. The strength of the AC will depend on the strength of the magnetic field, the speed of the coil rotating in the field. There's a few other factors, but yeah, that's basically how we do it. So this generates what we call a sine wave, rotating. It's a specific type of waveform, and it goes on forever. And we go from, as we indicated before, we went from zero to we'll call it positive, high positive, back to zero, then to the low negative, then back to zero. That's one cycle. The frequency of your AC is how many times this occurs in a second. In the US, standard frequency is 60 hertz. Some European countries, 50 hertz. But anyway, you've got two actual sine waves. You've got the voltage sine wave and the current sine wave, and as long as there's no impedance, there should be in phase. Not going to really slap any values on here because that could vary depending on what you're doing, but just be aware there are two sine waves. One's the current, one's the voltage. Anyway, so as we said, at 0 degrees, everything's zero, and then we move on to 90 degrees, which is the full positive voltage, full positive current, and from there moving on to 180 degrees, we have back to 0, and then at 270 degrees, we have the full negative current, and 360 degrees, we have 0 again. This is one cycle. 360 degrees is pretty standard for what we use with things like compasses and other things, but you should be used to 360 degrees in a circle, but yeah, that's how it works here. Now, by contrast, in the we have DC, we have a steady voltage at a specific value. It's easy to predict. We know how much it is. Like if it's 20 volts, it's always 20 volts. If it's 120 volts, it's always 120 volts. It's direct current. It's constant. At least we hope it is. However, AC is not constant. AC is a sine wave, and the voltage and current fluctuate in it, so we have to come up with some terms to refer to what we're specifically talking about when we say what the voltage or the current is. You heard 120 volts or 240 volts AC. What is that exactly? Well, we're going to cover that. So the first value we want to look at is peak-to-peak voltage, which is the maximum positive peak to the maximum negative peak. This one's not used too often, except when companies want to inflate their claims about the power of something. They might use peak-to-peak voltage, but generally not used that often. The next one in line is 0 to peak, since this is a sine wave and the negative and positive cycles should be the same. The negative part, the positive part, they should be the same, just mirror reflections of each other. We have what we call 0 to peak voltage, which is a lot more common. Again, you really don't use this a lot. Now, I should say, when you're calling something like voltage peak or current peak, VP or IP, I remember when I was at a Coast Guard Loran station, we said one of their propaganda points was 2.5 megawatts peak power. Well, that's 0 to peak. It's not actual power, it's the peak power. But yeah, like I say, advertising sometimes. But there are other ways to express AC, so let's look at the formula for average. If we take a number of slices of our sine wave and we average the voltage of each slice, then we add all those slices together and we divide by the number of slices. This gives us average of voltage. You can see the formula here for it. If you don't want to use math and we assume we're always using a sine wave, we can just say the average of the alternating current sine wave is 63.7% of the peak value. Simple. And for example, in the US, that would be around 110 volts. This was used historically a lot, but not so much anymore. Now, most of our voltage is done via, well, most of our AC values are done via what they call RMS, or root mean square, and you can see the formula here for root mean square. It's even more complicated than the average formula. We're not going to use it. Again, we're assuming our AC is a sine wave. And in a sine wave, the RMS value is 70.7%. And for example, in the United States, when they say 120 volts AC, they are talking 120 volts RMS AC, which is usually the current value used nowadays. You might have heard 110 volts, that's average, 120 volts is RMS. And okay, I'm not going to go into reactance and impedance, but I want to talk a little bit about them here. These all deserve a separate video unto themselves, but if you have an AC source, AC sine wave, we have two components, a capacitor and a coil or inductor that provide reactance, and impedance is derived from reactance. So for example, in our circuit here, we have a coil L1, which is measured, its inductance is measured in henries, but what we're after is the inductive reactance, which is X sub L equals 2 pi frequency times the inductance in henries, and that's measured in ohms. We use 60 hertz, so our frequency would be 60, and like I say, this will vary depending on your frequency. There's some interesting applications for this, which again, different video, but I just wanted to mention it. We also have a capacitor, and you'll notice capacitor is kind of opposite of the inductor or coil. It's measured in farads. And in this case, to get reactance, it's X sub C equals 1 over 2 pi Fc. So like I say, it's sort of the inversion of inductive reactance is capacitive. The inversion of inductive reactance is capacitive reactance, so to speak. And to get impedance, impedance is made up of two parts in an AC circuit, resistance and reactance. So we have the square root of R squared plus X sub L minus X sub C, that value squared. Again, we take the square root of it, and that equals, or impedance, or Z in ohms. I just want to mention these here. Like I say, that's a separate video, but it is a part of a circuit if these type of components are available, and there's some interesting stuff that works out from these equations. So the next thing I really need to talk about, like I said, if you want to know how to do the Ohm's law math, you're going to have to look at the older video, which I've linked here a few places. Anyway, we have a simple source. We have a load that's strictly resistive, so therefore, or impedance is 0, and we can go ahead and use Ohm's law like normal. The only thing you really need to be careful of here is your units. Again, we talked about various units for measuring AC, peak to peak, 0 to peak, average, or RMS. So if you're using a specific unit, you need to carry that all the way through. You cannot use current at peak to peak and voltage at RMS, or current at average, voltage at RMS, any of that. It has to be, if it's current RMS, voltage RMS, power RMS. So you need to be using the correct terminology, the correct factor through your whole equation. That's the really big difference between doing AC and doing DC in a simple circuit like this, is the what we're measuring the voltage as. And like I say, I recommend using RMS for most things and carry that through. So you have like your V with a small RMS subscript, or your I with a small RMS subscript, or even power with a small RMS subscript. But yeah, watch those units. All right, that was the whole shebang. Like I said, I didn't go into Ohm's law because I covered that in another video, but it still applies here. As I said, just watch your units. Future videos, if I do any more on AC, I'll want to focus on reactance and some of the interesting things you can do with that, the filters you can build, the tank circuits, low pass, high pass filters, band pass filters, notch filters. I will say that I've only used reactance and impedance a few times. That was back when I was working at the lab, and we were designing notch filters, low pass filters, high pass filters for various radio wave applications, and we had to use the those formulas for reactance and impedance quite a bit to determine what our notch filters should look like. And there's a few other formulas that go in there too, but yeah, that was the only time I really actually used those values. I mean, I remember when I went through electronics school, we had to calculate them ad nauseum, but yeah, never really used them out in the field. Anyway, that's the end of this video, so please like, subscribe, comment. It's actually a little rainy here. I'm back in Virginia, as you can probably tell, and like I said, I think I said in my last video, I've got my tickets to the Philippines, so out of here end of October, early November, and around that point, it might be a couple, 2, 3, 4 weeks before I start doing videos again, but after October, the next video should come from the Philippines. So see y'all later.